Hello. In this video, we're going to quickly talk about this JellyBags assignment. The purpose of this assignment is to practice with polymorphism and inheritance. And I wanted to use, first of all, something new, but also some data structures because you're familiar with data structures. Everyone can be more familiar with data structures. And there's some natural polymorphic and inheritance kind of situations that we can encounter, such as, for example, a stack or a queue could actually be represented as a vector, but some of the operations are different. With a stack, for example, you can only push and pop stuff at the right side of the vector, or add or remove elements from the right side of the vector. So it's like a vector, but it's more limited in its functionality. So you could define a stack as a subclass of vector where certain operations in the vector class are virtual, meaning they can be redefined in the child, but the other code doesn't need to know that it's actually a stack. It could treat it like it's a vector. And these special functions that are redefined would make the vector turn into a stack by the way the add remove operations work. So likewise in this assignment, even though these data structures are kind of different, they're going to be using an inheritance structure where everything is actually a bag. That's the parent class. And then the other classes are kind of special versions of the bag. So you're going to have a JellyBag class, which is a bag data structure. A bag is an actual data structure that people talk about. A bag can hold things just like a vector can, but the order doesn't really matter in a bag. It doesn't necessarily hold things left to right in the way you put them in. Also, bags allow repeats like a regular collection would. So a bag is just when you got some stuff that you need to keep track of, but you don't really care the order of that stuff. A set is like a bag, except it does not allow repeat elements, but also the order of the elements in a set doesn't really matter. A magic bag, I just made up, it's a type of bag. It can have repeats, but when you go through the elements one by one, the order of the elements could be random and you can have repeats, like it could give you the same element multiple times. And then a bean is like a bag, except you can only have one thing at a time. So if you put another thing into the bean, it actually will take out the other one, the existing thing. Otherwise, all these collections support the same functions. It's just exactly what those functions do might differ. So you already have some code on Delin that you're going to start by copying. And by copying, I mean make up your own folder for your assignment and then copy my files into your folder. Here's what you're going to be given. You have all the data structures are defined. They all function correctly. All you need to do is redefine the class such that it uses inheritance and polymorphism. So you don't need to come up with the way a bag is supposed to work or the way a set is supposed to work. That's all coded already. You just need to change how it's structured. So here's a bag. All of the classes are going to have these same operations available. So you can add something. I'll talk about what an item is in a second. You can add something. You can check if it contains that thing already. You can remove something. All of these return true or false. Add returns true if it's able to add it. Remove returns true if it found it. When you remove something, it only removes the first time. If there are multiple elements of the same kind, it will only remove the first one. You can get the size of the collection. And then when you want to go through the elements, you don't go through positions because everything's a bag. There is no position really. It's not like a vector. Even though it's going to use an array behind the scenes, that's not exposed to you. So if you want to go through the elements, you have to start by resetting the position. And then you have to ask in a loop, is there a next element? If there is, then you can get the next element. And every time you get the next element, the position goes forward. So because it's using an array, it will have the same order as you added things, but that's not supposed to be important. That's why we don't allow you to get a particular element at position 7 or something like that. So that's a bag, and then you see that all the code for the bag is here. It grows the array as appropriate and so forth. Now a set has the same operations, and it's going to use a bag behind the scenes. So a set adds or removes items to the bag and checks if the bag contains and so forth. When it adds, it makes sure the item's not already in there. So that's how it becomes a set, and so on. So they're all defined appropriately, and you can make and test. And what the test function does, it's not really using Google test. It's going to print what you should see, and then you see it, and you can just check yourself that it's correct. So all these test the various containers or collections. Then this is the part that's not going to work correctly until you do the assignment. It makes new pointers, but then it converts them into a regular bag pointer. If you had polymorphism and you had virtual functions and so forth, then when you convert to the bag will be the parent. We convert a bean to a bag, and then you say add, it'll actually use the bean's version of add, not the bag's version. But because this code has no polymorphism and no class inheritance, this function, which receives a bag pointer, will actually run the bag version of all of these functions because polymorphism is not going to be active. So all of this will behave like a regular bag. It won't behave like a bean or a set. So you'll see that in the output. This bottom output here shows that when it's a bag being passed into that function, it does everything it's expected. But when it's a set being passed in, it does everything just like it were a bag. And a bean behaves just like a bag. And a magic bag behaves just like a bag. So you don't want these to all behave with the same output. They should have the output that's described. So the assignment says, your task is to update the definitions of those classes such that they use polymorphism. All of these, set, magic bag, bean, they will be children of bag. When you do that, you get to eliminate a lot of code. For example, all these functions, which don't do anything special, just don't need to be in the set class at all. It can just inherit them. So the goal is to make your new versions as minimal as possible. Do not write any code that's not required. So once you turn on inheritance, you should take advantage of that. Allow your child class to inherit as much code as possible. Only redefine things that are different. Sometimes, by the way, you're going to need to call the bag version of a method, even though you're defining your own method. So for example, if you're in set here and you remove this stuff and you call add item because you know that it's not already in the bag, well, when you call add item, it's going to call yourself over and over recursively forever. It's going to crash. If you want to call the bag version of add, not your version, because you're a child, you're going to redefine what add does. But if you want to call the parent version, you just have to indicate that it's the parent version you want to call. So that actually kind of gets to the point that when you're turning a set, for example, into a child of bag, which you do by this, you are now a kind of bag, meaning you get to inherit these methods from bag. When you are actually turned into a kind of bag, you don't have a private data of bag anymore. When you turn the set to a child of bag, a set is a bag. So it's adding and removing things to itself. It's not adding and removing things to a separate bag. So this will be gone in your version. These functions add and remove to your own array, which is actually a private field in bag. So when you need to add or remove something to yourself, because when those operations are used on a set, you're going to tell your own code, your own remove, your own contains function to add, remove, and check contains and so forth. Only the ones you redefine are you going to need to call the parent version of that function. So these, since you're inheriting them, it will simply do the right thing. It'll add and remove to the bag, and you only redefine what some of these things like add are going to do, because they're going to be the only ones that are different. The last thing I want to show you is the makefile is pretty fancy. This makefile works in virtually any scenario where you have a bunch of CPP files. It uses these variables and patterns and so forth. So this says make a variable called source files that equals every CPP file in this directory. Make object files equal to take every source file, replace CPP with O. So pattern substitution. And so then you can say the main program depends on all the object files, which will be all the .o versions of the CPP files. This variable in the compile command means the target. This variable means all of the dependencies after the colon. So all the .o files will appear right here, and this will be the word main. In this version, it says anything that matches .o depends on .cpp, and the way you compile it is you say, I want to produce this .o file, and then this just stands for the same thing. It's the first dependency, so it'll just be the single CPP file. And then notice there's an extra option up here in the compile flags that are used in the compile command. This extra option produces these .d files. Those stand for dependency. So let's look at that. Here's set.d. The compiler produced this. It looked in set.cpp and noticed it includes these header files. So it's assuming, I guess, that to produce set.o, it needs all these files to exist. So what's happening in the makefile with this kind of command include, it's taking, for every .o file that is in the object files variable, it's including the .d. So all these, what's coming in is something like this. This and all the other ones are being injected into the makefile in addition to what's already there, so that it will say the .o file depends on these things. So you don't have to type them out, is the point. The compiler will look at the header files that are needed, and it will produce these into the makefile, so you don't have to type all that stuff out. And what you get is the proper behavior. So if you touch item, for example, all these depend on item, so they'll all get reproduced. If you touch set.h, only the ones that depend on set.h will get reproduced, and so forth. So that's a makefile trick. Also, one last thing, well, two last things, I guess. Item was just I was going to do polymorphism here, all different kinds of items, but I didn't. So we just have this one class called item that just holds integers. So nothing interesting is going on here. You don't have to worry about it. And just because I made a class, I then have to define what it means to be equal to another item and so forth. And then the last thing is notice these. Whoops. They're at the top of all the header files, because if you don't have these, you just have a regular header file and you do make, it will not succeed. What's happened here is it's tried to compile set.cpp. Set.cpp includes set.h, which also includes bag.h. Set.h has include item h, which means it's including this class jelly item definition. Bag.h also includes item h, which means it's getting this twice in the same. After all the includes are done, it sees the jelly item class twice, and it doesn't like that. So what we do in our header files is we do this if not defined, and then just put the file name, then define it, and close the if. So what happens is the first time this is included, because we're getting recursive inclusions, we're seeing things multiple times because different things are including the same thing. The first time it includes, this if is true because it says if not defined, this symbol. Well, this is the first time it's ever been included, so it's not defined. Okay, now go ahead and define it. It's not equal to anything. It just exists. It just says make item H exist as a symbol, and do all this stuff, and that's the end of the if. Then the second time it's included recursively, this has been defined, so the if turns out to be false. So all this that's inside the if is skipped. So it's a way of ensuring something is only seen once when it's possibly going to be included recursively. And it's a nice trick that avoids this issue. Now we don't have to worry about cycles of inclusions, and well, I think we do have to still worry about cycles. You can't have something include, you can't have A include B and B include A, I don't think. But this protects against double and triple inclusions because you're including different things that ultimately themselves include the same thing, and so you see it multiple times. So this is kind of a trick that we do on all of our header files. If you look at all the header files, they've all got this, just to be safe. Most of them don't need it, but just get into the habit of doing that. All right, so again, the code you're going to start with works. It's just this last output doesn't behave correctly. Your task is to redefine these children such that they are, well, these classes such that they are children of bag. Make functions in bag virtual as necessary so that these functions can override them and so that the polymorphism works correctly.